if you follow this link that's on here right now, you'll find the course material, which is on my GitHub page. And so all of this is available for you to download and modify and fork and everything else you want to do with the material. Let me really quickly before we start, I'll just kind of do an overview of the kind of technical aspects of the installation. The idea of this tutorial is that you can follow along and execute code and try things as we go. And in order to do that, you'll need the IPython notebook. Hopefully you've installed Anaconda like the conference organizers recommended, and if so, you have the notebook. And you can download all this material for this course here. If you don't want to, or if you're unable to run the notebook locally, one way you can view all the material is by clicking this link at the bottom of the first README page. This view the tutorial materials. Let me make this a little bit bigger. And if you click there, you get to something called the NB Viewer service. And essentially what this does is it gives you static representations of all these notebooks. If you run the notebooks locally, you'll have dynamic representation where you can actually execute code and modify code and things like this. The static representation on NB Viewer is just something where it's read-only and you can see what's going on and follow along that way. So what I would recommend is that you, if you use Git, if you have a GitHub account, you can use the Git clone address here to clone everything. Otherwise, you can download a zip file with everything inside it and go from there. So hopefully you've all had a chance to take a look at that and do it. If you're wondering what the address is, I'll put it back on the screen right now. github.com/jakevdp/sklearn_PyData2015. So I'll leave that up there just so people can find it. So briefly, what I'm going to try to do in this next 2 hours is we're going to talk about, we have essentially two goals. I want to talk about the basics of machine learning, like what machine learning is and how you should think about machine learning when you approach some sort of problem with data. How to format your data, how to frame the questions, and how to think about it in that case. The other piece of it is actually doing machine learning in practice, and we're going to be looking at the Scikit-learn library. So you can get an overview of that if you look at scikit-learn.org, scikit-learn.org. I think that's it. Or is it just, oh yeah, it's working. My connection is just slow. If you go to scikit-learn.org, you can see all the information about this library. There's pretty extensive documentation, tutorials, and things like that. And essentially what scikit-learn is it's a library that strives to have really fast, well-documented, well-designed implementations of standard machine learning tools. So most of the common machine learning things you'll find out there are implementations in Scikit-learn, and that's why it's a great library to start with, because you can just use it. If someone tells you, I want to do a kernelized support vector machine or something like that, you can go into Scikit-learn and you can find that algorithm and you can use it once you know the syntax of how to use it. Okay, one other thing I should say, once you have this downloaded, let me open a new window, basic, and make this bigger. Once you have this downloaded, if you go into the directory where this is, I'm hoping if you have Windows, it might look a little bit different. If you're on Linux and Mac, it'll look a bit like this. And you run IPython notebook, assuming you have IPython installed there. Then what should pop up is this. This is the dynamic notebook version that I was talking about. You pop up this thing and you can click on notebooks and you can go in and see the content. And here's that nice URL page that I was using. So hopefully you have this material in front of you either in the form of the dynamic notebook or in the form of that static view. And we'll jump right in and take a look at it. Oops, I'm using a different notebook version. So let's start with the preliminaries. Like I said, the goals of this tutorial, I want to introduce the basics of machine learning and then introduce the syntax of scikit-learn. This is about the schedule that I'm going to try to stick to. This first 15 minutes is preliminaries, setup, introduction, the stuff that I've been talking about up till now. The next 45 minutes or so, until about 11 o'clock, I want to talk about the basic principles of machine learning, define some terms, help you to think about the vocabulary of what we're going to use, and also the basic Scikit-learn interface. So that's about 45 minutes that we'll cover this. Then we'll take a short break, 5 or 10 minutes, so you can get up and stretch and grab a beverage or something. And then the last hour, I want to go in depth into two interesting supervised techniques, so support vector machines, and then something called random forests. And then I should add on top of that if you look at the index notebook here, that basically covers this parts 1 and 2, preliminaries and then the introduction. This is I have about 6 hours of tutorial content here. And all of this I've included this in the directory, not because we're going to get to it in these 2 hours, but because if you want to go back and learn a little bit more and read a little bit more, you can go read that on your own afterwards. And there's some videos floating around online of me doing the full 3 or 4 or 6 hour tutorial. You can search for that too if you really like hearing me talk. So all of that is there in that material. So the preliminaries, these are the packages that are required to run all the commands in here. Python, you can use either version 2 or version 3. I try to be inclusive that way. And all the code in here should run on version 2 and 3. And then there's things like NumPy, SciPy, Matplotlib for plotting, Scikit-learn, of course, IPython for the notebook, and Seaborn is this nice little library that helps makes your Matplotlib visualizations a little nicer. So I tend to use that to make it nice. And if you have Conda installed, you can do this by just running this line, Conda install all these packages. And once all that is installed, you should be able to just run this code within your notebook and see all the versions of the various packages that you have installed here. So IPython, NumPy, SciPy, Matplotlib, Scikit-learn, and Seaborn. And finally, down at the bottom, I just wanted to leave you with some useful resources if you want to learn a little bit more about this stuff. I know I'm kind of starting this from the assumption that you're comfortable with Python and comfortable with a lot of the scientific tools. So some of it might be moving a little bit fast if you haven't used NumPy or haven't used Matplotlib in the past. But you can look at some of the tutorials on these sites if you want to come back to that later. So any questions on just that preliminary stuff before we jump into the material? All right, I think we're good to go. Now, usually these tutorials I try to make them interactive and a lot of question and answer. It's harder in a big room like this. I'm used to having more like 30 or 40 people, but feel free to raise your hand and interrupt, and we'll do our best with that. So let's go back to I'm going to leave this page, go back to the index, and I'm going to open up this 2.1 notebook right here. And let's take a look at this. That notebook converted thing that comes up is because I'm using a newer version of IPython, and the notebooks are an older version which work with everything that you might have installed. So machine learning in Python. Like I said, the main goal of this first section is going to be to get a definition of machine learning, to learn about how to represent data for Scikit-learn, and to learn about how the Scikit-learn API itself works. So I went through a little bit of this. Scikit-learn is a Python package that's designed to give you access to well-known machine learning algorithms and have a clean, well-thought-out API. That's the big part of it. So once you learn how to use one algorithm in Scikit-learn, you can basically apply that knowledge to use any of them. It's a kind of a drop-in replacement for all the different algorithms. So the main question, though, here is what is machine learning? And machine learning is one of these terms that gets thrown around a lot, and it has kind of this magic connotations, like, oh, how are we gonna do this thing in our software? Oh, we'll just use machine learning; it'll be fine. And machine learning, essentially, what it is it's a set of models that have tunable parameters, and you can tune those parameters to adapt to previously seen data, so that then the models can generalize and make predictions about data you haven't seen yet. So machine learning is just modeling. It's about building a model of your data that can then tell you about what's happening with new data that comes out. And we'll see an example of this. And two very simple machine learning tasks are classification and regression. So let's take a look at a classification thing. And I'm gonna start by clearing all the output just so we have a clean slate here. First thing I'm going to do is import some stuff that we need to make the figures appear in the notebooks. You can read about this in other places. And then I'm going to plot this little diagram right here. So this is an example, a quick example of a machine learning application. So the idea is that we have two clumps of data. We have one clump that's labeled blue and one clump that's labeled red. And we want to train a model that will distinguish between those, right? And the model that we've trained is this line that we draw down the center. And that line has a margin that kind of separates the data. And so now the idea is that if we were to drop another point on here that we don't know what it is, if it drops up here, that model will tell us it's likely to be a blue point. And if it drops down here, the model will tell us that's likely to be a red point, right? And this might seem incredibly simple, right? Simplistic even. Like you could just look at this data and draw that line yourself. Why would you need an algorithm to do it? And where this becomes more powerful, though, is when you start looking in higher dimensions. So this is two-dimensional data. But we might be looking at 1,000-dimensional data or 10,000-dimensional data, right? And at that point, it's very difficult by eye to draw one of these separating lines. Actually, in 1,000 dimensions, you're not drawing a separating line. You're drawing a 999-dimensional hyperplane that's separating your data, right? So I challenge you to do that by eye or by hand. That would be hard. But the cool thing about the machine learning algorithms is they work in 2 dimensions, but they also scale up to these large number of dimensions. So it means we can do things like separate 2 clumps of data in 1,000 dimensions if we want to, and it'll do this automatically. So that's a classification task, and what distinguishes a classification task is that there are discrete labels. We have red or blue. We don't have a continuous array of color labels. It's just one or the other. So these discrete label problems are classification tasks. And just to prove to you that this is actually a machine learning task, we can load the code that generates that figure. And you can see what I'm doing is I'm generating some blobs of data. I'm actually training this SGD classifier, which is a stochastic gradient descent classifier. And then I'm plotting the results, and I'm doing a contour of the classifier levels here. So it's actually a machine learning operation that generates this plot. It's not just, I didn't just draw it in Microsoft Paint or whatever. Okay, so that's a classification task. The next task that we might talk about is a regression task. And what distinguishes a regression task is regression is when you have a continuous label. So this is a different type of data. We have X data and we have Y data. And what we're saying is this Y data on the vertical axis is the continuous label of our data. So to be more concrete, this continuous label might be something like, my background is in astronomy, so it might be something like the distance to a galaxy. If you're wanting to learn the distance to a galaxy based on some observations, that distance is this continuous value. And again, what machine learning does is it generates a model based on data that you've seen so that you can generalize to data that you haven't seen. And here the model that we're drawing is just a straight line fit to the data. What this says is that given an X value, we can go up and ask where the line hits, and that tells us the prediction of the Y value, right? So really simple stuff. You did this in your, first grade statistics class, fitting a line to data. But fitting a line to data really is a machine learning application. And again, this might seem really simple, right? Everyone's fit a line to data at some point. Why do we call it machine learning? But where this sort of idea becomes more useful is when you're looking at high dimensions. So what if you have, rather than one observation, one X value, what if you have 100 X values? What if you have 100 observations of each of those galaxies, and you want to figure out some way to turn those observations into an estimate of the distance to the galaxy? And that's what regression can do for you. And again, instead of drawing a line through the data, it would be something like drawing a hyperplane through the data, right? And the machine learning, the algorithms we'll talk about actually scale up to that. Okay, so that's classification and regression, and those are the two essential things that essential algorithms we're gonna talk about. Classification for discrete labels and regression for continuous labels. A question? That's a good question. So the question is regression always linear? And the answer is no. We can do lots of nonlinear things, and we'll actually see a couple examples of those later on. So we're not always doing something simple like fitting a line to data. We're not always doing something simple like drawing a line. They can be more complex boundaries as well. Thanks. Any other questions before we move on? All right, so that's the basic stuff we're going to be covering today. And now I want to jump into more detail about how you'll actually make this happen. Okay, so the first thing is to try to figure out how to represent your data in Scikit-learn. So you have some data set. You need to munge it and transform it so that the Scikit-learn algorithms can work on it. And essentially in Scikit-learn, all the data that you're going to be using will be in the form of a two-dimensional matrix. So this matrix will be, the number of rows will be the number of samples in your data. And by samples, I mean distinct objects that you're interested in learning about. So in my example from before, the samples would be the galaxies themselves. So taking a look at the galaxies, or you might be looking at classifying images. The samples in that case are the individual images that you're looking at. And so that's the number of rows in the matrix. The number of columns in the matrix corresponds to the number of features. And what I mean by features are, each feature is an observation that you have of every sample in the data set. So for the galaxies, I might have an observation of each galaxy through a red filter, and I might have an observation of each galaxy through a blue filter. And we have these numerical quantities that we observe for every object. So what you end up with is a matrix that's number of samples by number of features, and that's what gets plugged into the algorithm. So sometimes generating that numerical matrix is the difficult part. Like for example, if you're trying to classify text documents, classify articles you pull off online, you have to do some tricky things to turn those words into some sort of quantitative numerical feature that you measure. And there are things you can do like asking for how many times a certain pair of words shows up in the document and things like that. So, but as a very simple example, let's take a look at kind of this classic data set from machine learning. Oh, I see a question right there.
Yeah, I might be jumping a little bit ahead, but would you be covering the different ways of converting the categorical? Sometimes already recorded, sometimes not.
Yeah, I'm not going to be going into, the question was, am I going to be covering transforming categorical or text into numerical? I'm not going to be going into that, but if you look on the Scikit-learn website, there's some information on that and some tutorials on that. So in particular, there's a pretty good machine learning on text tutorial that you can use. But the more simple data set I'm going to look at is this classic one in machine learning that for some reason someone back in the 70s decided to use, and everyone's been using it since then. So who am I to break the trend? This iris data. So the idea is that we have three observations of three different species of irises. So this is one species right here. That's what it looks like. Here's another species right there. Yeah, it looks a little bit different. And here's another species right here. So these are three species of irises, and we want to train an automated classifier that will identify these irises based on these observations. So a couple quick questions here. So we need an array of number of samples by number of features. So what does number of samples refer to? What are the samples here? Flowers, yeah, so individual flowers that we observe are the samples. So each row of the matrix will correspond to one flower, right? And what about the features? So the features are data, they're things that we observe about each sample. So what might some features be that we could use with the irises to identify them? Number of petals, yeah? Like color, shape, yeah, maybe length of petals or width of petals, things like that. So yeah, so this is the idea. Whenever you're trying to classify or do some machine learning on something, you have to figure out what are the most useful features that you want to include. So this is the point when your own expertise in the problem comes in, this feature engineering. So for me, as an astronomer, if I'm trying to use machine learning on an astronomy data set, I need to think about what I know about astronomy and think about what features might be worth observing. If you're doing something like trying to maximize click rates on some web page based on features about a user, you probably have some intuition about what sort of users are on your website and what sort of features you'd want to plug into these algorithms, right? So this feature engineering thing is something that every intro machine learning tutorial will brush over completely, but it's actually the most important part, right? And the reason we brush it over completely is because every one of you in this room has a different area of expertise and a different domain where you're going to want to be applying this stuff. So it's hard for me to give general guides on choosing features because it's more about you knowing the field that you're using and choosing the data that you think is going to be relevant. Yeah.
How might principal components be applied to this choosing features?
Yeah, that's a good question. So he mentioned this algorithm called principal component analysis and asked how you might use that to choose features. So there are algorithms like principal component analysis and others that will let you select among a group of features which ones are most important in some sense. But you still have to give it a group of features to start with, right? So you still have to use a little bit of your own intuition to figure out what features to start with. But good question. PCA, principal component analysis, is one of the things we won't get to in this 2-hour tutorial, but if you look at the extended version, there's some material on that in there. So for this classic iris set, basically what has been done in the past, or what data has been used, is you have the length of the sepals, the width of the sepals, the length of the petals, and the width of the petals. So for each flower, you have these 4 observations. And these observations are because some botanist went out in the field with a ruler and started measuring these flowers and got a couple hundred of them. And then what we want to predict labels. And these labels are the species of the iris. So we have iris setosa, iris versicolor, and iris virginica, which I showed up here. These are the 3 different species. So Scikit-learn includes a bunch of data sets, and one of the data sets that it has for experimenting with simple data is this iris data set. So we can load it, and we can look at what keys are here. We have the target names, the data, the target, etc. And if we look at the data itself, the data is 150 samples, that's this entry right here, by 4 features. So we have 150 flowers. We're looking at these 4 measurements. And if you look at a single row of the matrix, here we're looking at the first row of the matrix, we find that this one has a sepal length of 5 centimeters, a sepal width of 3 centimeters, and et cetera. So this is kind of the fingerprint of this iris. This is the data that we have about this one sample. And the other thing we can look at is we have, here's the iris data again, 150 by 4. The iris target is just a vector of length 150. And this is a numerical code that tells us what species it is. So we're saying it's either a label 0, label 1, or a label 2. And if we want to convert those labels into names, we see that 0 is setosa, 1 is versicolor, and 2 is virginica, right? So essentially what I want you to see in this is that when you're taking your data and turning it into something that you're going to use in Scikit-learn, you want your data to be in this 2-dimensional array, that's the number of samples by the number of features, and you want your labels to be in a 1-dimensional array that is number of samples. So each sample has a label. All right, so that's the way to think about how to get your data into these machine learning algorithms. So now I'll really quickly here's some code here. This is mostly matplotlib code that helps plot things. And here's a visualization of two of the features that we're looking at. We're looking at sepal length here versus sepal width here. And then the colors show you which iris species it is. So we can see that there's from this, we can see that we should be able to draw some sort of line or some sort of boundary that here would distinguish the Setosa from the others. But the Virginica and versicolor are a little more mixed, right? And it might be that if you change the index, if you look at different pieces, different variables, you might be able to find better separations. So right now, I want you to take just a moment and look between the different dimensions here. This is 0, 1, 2, and 3. You can plot these against each other and kind of see, just get a feel for whether you think an algorithm would be able to separate these. And if you have your IPython notebook up, you should be able to run this. We'll take a couple minutes and look at that. This is part of the data visualization and data exploration part of machine learning, which you really want to, before you just start blindly throwing algorithms at your data, you want to visualize it and understand what's there and maybe figure out if there are issues. Because sometimes you find weird things in data. Like I was doing just for fun, looking at some census data about birth rates versus age of mother and father. And I did this aggregation where I found the average mother age as a function of month and average father age as a function of month. And the average father age was like 20 years older than the average mother age. And first I was like, whoa, this is crazy. I mean, there's this weird age gap. And then, when I looked closer at the data, I hadn't actually visualized the raw data. And when I looked closer, I found that if they don't know who the father is, they put in his age as 99, right? So. Yeah, so it just means that there are a lot of fathers that were unknown in those months. So anyway, you got to visualize the data and you got to figure out what's going on. So did anyone find a good combination that really separates these pretty well? Yeah.
Petal length by petal width.
What are the indices on that?
Sorry,
2 and 3. Yeah, oh cool. Yeah, so you can see here if you look at petal, just the width and length of the petals, the Setosa is completely different than the others. And then these two are even pretty well distinguished. So we would expect here that an automated classification should be able to do pretty well, right? And we'll get to that in just a second. We'll take a look at doing this automated classification. But first I want to show you that there are lots of other data sets here. So if you import data sets from Scikit-learn, you can use this cool feature of IPython that's tab completion. So you press tab and you can see there are things like 20 news groups. So this is text data. There are LFW, which is labeled faces, labeled pictures of faces. There's Olivetti faces. There's species distributions. And then also there's the load data. Fetch data is actually pulling things from the web. Load data is stuff that's included with the package. So we have iris, we have sample images, all these other things. So there are diabetes digits. So there's some nice data sets that you can play with, and we'll see a few of those. And in the next section, we'll take a look at some of these data sets and do kind of a basic machine learning thing on them. So before we move on to the next section, any questions about this, about the data representation? This number of samples by number of features matrix is kind of the fundamental thing that I want you to get out of there. Yeah?
A lot of these Scikit-learn data sets seem to be sort of dictionaries of arrays. Is that a common pattern? Or?
Yeah. So the question was these data sets that are in Scikit-learn seem to be dictionaries of arrays, and that's just because it's a convenient way to store them, right? Because you need the data matrix, you need the labels matrix, and then you need some metadata. So Scikit-learn just stores that in a little dictionary. And if you're doing your own data, you don't need to construct that dictionary, you just need to construct those arrays, that matrix and the label array. All right, well let's take a look at the second part of this first morning session here. I'm going to, again, toggle the toolbar and toggle the header. And take a look at the basic principles of machine learning. All right, so we saw that the difference between classification and regression, right, which is those learning examples. We saw how to make our data fit in Scikit-learn. I need to clear all the output again. Oh, but I zoomed in too much. Here we go. Okay. So in Scikit-learn, when you want to do some machine learning, what you're going to use is this estimator object. And if you're familiar with Python, Python is an object-oriented programming language. You can define classes. And what Scikit-learn does is that each type of model, each type of learning model is its own class. And so for example, if we want to do a linear regression like we saw earlier, fitting that line to data, we can import from scikit-learn.linear model, we import the linear regression class. And then our model is a linear regression class with some sort of hyperparameters. So we're going to say we want to normalize linear regression. And we get out this model object that has an attribute normalize that's true, right? So if we print out the model, we see all these attributes. So this is a linear regression model. It's going to copy the data before modifying it. It's going to fit an intercept to the data, and it's going to normalize the data. So a type of model is a class, and the model itself is an instantiation of the class in Python. So that's true across the board in scikit-learn. Now, for example, let's say we have some data, and the data looks like this. We get some x and y values, and we plot them, and we just have this straight line. And now, if we want to actually fit the model to this data, what we need is we need our data matrix, which is number of samples by number of features, and we need our label matrix, right? So in this case, the number of samples we have is just these x values, and the labels we have are just the y values, right? Where the labels are kind of the dependent variable here. So what we need to do is we need to take our input data and reshape it into this 10 by 1 array. And then we have our labels, it's just a length 10 array. And this is just a NumPy formalism to reshape an array like that, to add a dimension. And once we have that data in the right format, we can fit our model to it by calling the fit function, the fit method. And we see that it returns itself. So now we have a model that's fit to the data. And then once we've fit the model to the data, there will be these attributes that have an underscore after them. And in scikit-learn, any attribute that ends with an underscore is one that depends on the data, that was learned from the data itself. So we can see here that our fit coefficients were 2 and our intercept is 1. And if we go back to how this data was generated, we can see that we did y equals 2x plus 1, right? So we put in simple linear data, and this model looked at the data and pulled out the slope and the intercept that we put in. And there are other things, like you can look at the residuals around the fit. And here, since the model fits the data perfectly, the residuals are essentially 0. 10 to the minus 31 in double precision is basically 0. So that's how the scikit-learn model looks. Again, you have the class name that defines the type of model you want to use. You have the instantiation of the class, which is the actual model you're going to fit to data. And then this fit method here, which actually applies the model to data and does some sort of internal calculations to create these internal variables. Right? So any questions about that? That's just the first very basic scikit-learn estimator. And every time you do a scikit-learn problem, it'll look like that. It'll be import a class, instantiate the class, fit it to data, and then do something with the model after that. So we briefly saw this before, the classification and regression. But classification and regression are examples of what's called supervised learning. And when I say supervised learning, I want you to think about basically labeled data. When supervised learning means you have labeled data and you want to predict the labels for some other data. So some examples of supervised learning are things like if you have a multicolor image of an object, you want to figure out whether that object is a star or a quasar or a galaxy. That's a supervised problem. Given a photograph of a person, identify the person in the photo, right? If you had enough data and you had the right model, you can do that sort of thing. And then there are things like recommender systems where you have a list of movies someone looked at. You tell them what other movies that they might like. Netflix and Amazon use things like this. So we saw a quick classification example earlier, but now I want to actually walk you through what you do in Scikit-learn to do a classification. So we're going to go back to this iris data set that we were looking at. And remember, the X is the 150 by 4 matrix of data. The Y is the labels. So the first thing we're going to do is we import. Here we're going to do a k-neighbors classification of iris. So we import the neighbors module. And then we instantiate the model and we tell it that we want to look at the 5 nearest neighbors of each object to figure out what it is. Then we fit the model to data. Call fit on X and Y. And then what we can do is we can call the predict method and ask it, well, given this observation with a 3 by 5 sepal and a 4 by 2 petal, what's the predicted target name for that? So we do call the predict method, and what we get out is this result, which is an index into the target names, and it tells us that this iris is a versicolor. Right, so again, the pattern that I want to get into your mind is that you're importing a model, you're instantiating the model, you call fit to the data, and then here we call predict on new data, and it tells us what the label is. Here the new data is measurements of a flower, but your new data could be whatever it is in your application. You can also do things like probabilistic predictions. So this predict probability says that it's a 0% chance of being the first label, an 80% chance of the second label, and a 20% chance of the third label. So this predict and this predict proba are some of the methods that you'll see in machine learning fairly often. And I just have this little code that actually shows us on the plane of sepal length versus sepal width. It essentially shows us what this algorithm is doing. It's looking at if you drop any point on here, it's asking what are the nearest 5 neighbors of that point, and it takes a majority vote among those and then calls it that color. So, right here, this point, you look at the nearest 5 neighbors of that, and most of them are green, so it's going to call this green. And that means it misclassifies that blue point, but that's the nature of the model. So again, I'm repeating this over and over, but I want you to get this. You import the model, you instantiate the model, you call fit on your data, then you call predict or predict probability on your unknown data, and you get out an answer. So now I want to give you a chance to try this out. So there are some other estimators, and for example, there's one called sklearn.svm.svc. And SVC stands for Support Vector Machine Classification. So I want you to take a minute or so and just create an SVC model and fit it to this data and predict what that data point is with the SVC model and see if it agrees with the k-nearest neighbors. Just to get some fingers on keyboards. This is pretty simple, but I want to get you used to instantiating the class, calling fit, and then calling predict. Okay, so I typed it up here. It's just a few lines of code, right? You instantiate the model, and in here, if you want to, you can set some of the hyperparameters, the C or the kernel or the degree or things like that. We can get to that. We'll get to that later. You fit it to the data, the X and the Y, and then you can predict on anything. Here, I just decided to predict on the first 5 points of the data, and it says the first 5 points of the data are zeros. And just checking against the actual labels, we find that the first 5 points are zeros, right? So I'm going to do the first 50 points if we want, and take a look. First 50 points are zeros. Let's do something more interesting, like every 10th point, so we actually get some differences in there. Yeah, so it looks like the support vector classifier is doing pretty well on this data set. This isn't a great way to check whether your classifier is doing well. You should take a look at things like cross-validation if you actually want to do that. And again, that's something we won't get into these 2 hours, but in the extended material, it's out there. But this is basically the syntax. You're fitting the data, and then you're predicting on some other data, and you get out a result. You can compare. So similarly, we can take a look at a regression example. So that was a classification, where classification is where you have discrete labels, right? In a regression example, we have continuous labels. And here's some noisy data where we have some X values and Y values, and we want to predict given an X value, what we think the Y value might be. So let's do it with a line of best fit. This is really simplistic, but it's a good model to start with. So we already imported linear regression above. We instantiate the model, we fit it to the data, and then we figure out some data that we want to predict on, and we predict on that data with the predict method, and then we can plot the two. And we see that this is our linear regression model to the data, right? And again, it's the same pattern as in classification. We fit the data, we predict on unknown data, and then we do something with those predictions to compare them. So this is our linear regression model. Not all that great. We can also do more sophisticated models, and this gets to the question that I heard earlier about whether we can go beyond linear regression. So let's take a look at the random forest model. This is a really flexible, non-parametric model. This random forest is actually one of the two, I think, most important machine learning models in practice right now. If you ask people who are actually doing machine learning for a living, a lot of them will say random forest is really good. And if you want, on Sunday morning, there's a keynote, or Sunday afternoon, there's a keynote from Josh Bloom, who's an astronomer at UC Berkeley. And he's kind of made his mark in astronomy by applying random forest to astronomical problems, and has done some really, really interesting work in that. So he'll probably talk about it a bit. He actually spun off his astronomy work into a startup that's all about they started out just doing random forest as a service, essentially, and then spun off and diversified a little bit. But they have this interesting startup called Wise.io. Anyway, so we instantiate. This is the cool thing about Scikit-learn. We've done the linear model. Now all we have to do is basically replace this linear regression with random forest, and everything works the same. So all I've done is I've used the random forest model instead of the linear regression model. We fit it to the X and Y. We create our unknown data. We predict the data, and then we plot the results. And this is what our random forest model does with this data. So you can see the random forest is a lot more flexible, right? It's basically following these weird contours in the data set as they go up. And the question would be, is this a better model than the linear model? And the answer is a very definite, it depends, right? Because if you think your data is a linear model with lots of noise, then the linear model might be better. If you think that these deviations from the line are actual information in your data and not just noise or uncertainty, then you might want a more flexible model like a random forest regression. And again, to make that choice more quantitative, you can do things like cross-validation. Model selection is a big topic that we're not going to get into today, but it's in that extended tutorial information if you want to read about it. But the point here is that all we had to do was drop in this replacement, right? If I make this a linear regression, we get back that data right here. And if I make this a random forest regressor, we get that data. So it's all, this is the strength of scikit-learn. You can drop in models, you can replace one model with another and use the same code and kind of see how things change. And it makes it really nice to compare lots of different models. Yeah, question?
Yeah, you've called a number of models at this point, but you really haven't talked about choice of hyperparameters for those models.
Yeah. So that's another thing. There's this hyperparameter question. So he was asking about hyperparameters for models. So you can do things like you can specify the number of estimators you want in the random forest. And that'll change the results, right? If I do 1,000 estimators, then things are a little different than if I have 10 estimators. Oh, actually, they look the same, don't they? Maybe I want to do, I should do something else that actually changes things, right? Max depth, let's do max depth equals 2, and then this is what it looks like. And if we do max depth equals 20, then this is what it looks like. It's a lot more. So anyway, that's all to say that there are these hyperparameters in models that you have to set. And this is another piece that to really understand hyperparameters quantitatively and decide how to set those, you need to do something like cross-validation and model selection. And in a way, it's the same as choosing random forest versus a linear model. It's the same sort of procedure as choosing random forest with max depth of 20 versus random forest with max depth of 1, which just does something like this, right? So unfortunately, I'm not going to have time to get into the validation today, but that's something that's really important that if you're going to use this in practice, you should look into and learn about a little bit. So actually, this is what this exercise is. I want you to take a look at this and start looking into what these hyperparameters are. You can do this, you can see all the hyperparameters if you, in this IPython notebook, if you do random forest regressor followed by a question mark. It'll pop up a documentation thing that shows you all these different things that you can do. And I just want you to take a few minutes now and modify this code, modify the hyperparameters, and see how it changes. You know, see if you can make a more complicated model or a more simple model. And we'll, in the second half, we'll talk about more what these hyperparameters mean. But for right now, I just want you to, try it out to see what comes out, and it's good to experiment that way. So go ahead. Yeah, another question?
Can you change the hyperparameters after the model's been instantiated, or do you have to set them at instantiation?
Oh, that's a good question. Can you change hyperparameters after the model's been instantiated? Sometimes you can, but it's not a good idea because it doesn't always. Actually, I take that back. Yeah, you can change them pretty safely after they've been instantiated. So we could do here. We could do model.maxDepth equals 20 after we instantiate it, and it should work. Yeah. Another question?
Are the hyperfilling parameters the only means of preventing overfitting, or can we introduce some sort of regularizations?
Yeah, that's a good question. So he was asking about the idea of overfitting versus underfitting and the hyperparameters as a way to tune that. Hyperparameters are the main way that you do that. There's also, you mentioned regularization. There's also regularized models you can use. Like if you look at from Scikit-learn, import linear model. And if we look at linear model.linear regression, let's see, what am I looking for? There's this linear model.ridge regression, and there's also lasso regression, which is, these are different forms of regularized linear models. So if you know about regularization, that's what you can look at. Regularization in a sentence is just a way to make sure a model isn't overly complicated and doesn't fit the noise in your data. Yeah, another question. Yeah, here in random forests, n estimators is the number of trees that you use. So if you want to use 100 trees in your forest, you n estimators equals 100. You can do 1, and then you get weird stuff. If I do n estimators equals 1 and max depth equals 1, we'll have a really, really bad model. Oh, I guess that didn't even, huh. I thought that would be even worse. What's that? Yeah. Oh, yeah, that's the problem. Thank you. Yeah, so that's a single tree with a max depth of 1. It just splits your data into 2. So we'll see how that works. So yeah, so this is the idea. When you're playing with these models, you should really think about hyperparameters and how they work. And the fact that each model that you're looking at, when you import, say, random forest regressor, this is not a single model, but this random forest regressor here defines a class of models. And to pull a single model out of that class of models, you instantiate it and you specify the hyperparameters. So just to reiterate, a random forest regressor with different hyperparameters can be as different as, say, a linear regression and a support vector machine. You can just have vastly different models depending on the hyperparameters. So remember that these classes are classes of models, and the instances are the actual models themselves that can be varied. Yeah?
So you mentioned that random forest is like a pretty important model. So do you have a recommendation of the best way to visualize these trees or how
Yeah, so in the second half, we'll go a little more in depth on random forests and hopefully be able to address that question. But right now, we have a couple minutes before the break. So I have this section introducing unsupervised learning. So I said supervised learning is where you have labeled data. Unsupervised learning is when you have unlabeled data. Like you just have data out there and you want to learn things about it, like how clumpy is it, or how many intrinsic dimensions does it have? I'm not going to go through that right now, but it's an interesting thing in itself. And then the third thing that I'm not going to go through right now, but there's details that you can read later, is this model validation. And this is the question of how do you choose the best set of hyperparameters, or how do you choose the best model? And you have to decide carefully on that to make sure that you're not overfitting your data or underfitting your data. And there's details about that. But I'm going to skip that right now. And then this last 5 minutes before our midway break, I want to show you a quick application of machine learning to a more interesting problem. And this is taking a look at handwritten digits. So this is one of the data sets that's included in Scikit-learn. You can load the digits data set. And here's some code that will plot them and take a look at what we're looking at. So this digits data is, there's about 1,800 samples. And each sample is an 8x8 image that looks kind of like this. So each of these is an 8x8 pixel image that has a handwritten digit. And they're all normalized and put on the same grid. And so you can look at these digits, and this 8x8 pixel image is essentially 64 observations of each digit, right? If you stretch out those 8x8 pixels, you get a length 64 vector. So you can think of these as each of these as a point in a 64-dimensional space. All right, so this is a way that's common to think about data in machine learning. You think about each sample as a point in a high-dimensional space. And in this case, our points are intrinsically 64-dimensional because there's 8x8 pixels. So here's what the data looks like raw. So here's the pixel image, and you can see that this is a 0, right? Because it has high numbers here. It has no ink in the middle and no ink on the outside. And if we look at the data itself, the data is length 64, and it's just a vector of 64 values. And the target, again, is the values that we're trying to predict. So 64-dimensional data is difficult to visualize, right? I don't know of any plotting package that easily does a 64-dimensional plot. But you can do 2-dimensional plots, right? So one of the first things we do is with an unsupervised learning algorithm, we can take those 64 dimensions and ask what is the most important combination of two dimensions. So we're basically reducing these dimensions down from 64 to 2. And here we'll use an algorithm called isomap, which you can read about, but it basically is able to do a nonlinear projection of however many dimensions the input is to n components of 2, to 2 dimensions. So now we see that we have this projected data, which is 1800 by 2, and those 2 dimensions somehow encode all the information of the input in some way. And if we take a look at these projected dimensions, we see something really cool. And I really love this plot because you can look at things like it tells you that zeros here in black are very, very different than any other digit out there. And that makes sense, right? Because zeros are basically like they don't have any ink in the middle, and pretty much every other digit out there will have ink in the middle. So you would expect that zeros could be pretty well distinguished. But then over here it gets a little more difficult. Like for example, this teal here is 3s, and this red here is 8s. And if you think about 8s versus 3s, they kind of have similar features, right? So you can see how an algorithm might get confused between a 3 and an 8, and they actually overlap in this projected space. So this gives you some intuition about whether a classifier would be able to easily separate out these digits. You'd expect that a classifier would probably be pretty accurate at identifying zeros, but then the zeros overlap with the 6s a little bit, right? Because if you draw a 6 in a sloppy way, it ends up looking a little bit like a 0, right? So this is just a cool way to see what's going on in the data. So now we can do a classification, and what I'm going to do is split the data into 2 pieces, a training set and a testing set. And this makes it so that we can test the result on data that the algorithm hasn't seen yet. And I'm going to use a logistic regression because it's pretty simple. We'll instantiate the classifier, fit it on the training data, and then predict on the test data. And now we can use some of these scikit-learn metrics and say, what's the accuracy of our predictions? And here we find that with just that simple algorithm, we get 95% accuracy in identifying these handwritten digits. And we can go a little bit further and ask, like, what digits did we get confused? So here's the predicted label versus the true label, and it shows the density of predictions. So here, for example, we confused 3s with 7s fairly often. And we confused 1s with 8s fairly often. So this gives you an idea of what's going on inside the algorithm itself. And then the other thing we can do is we can actually plot up some of the outputs along with their predicted labels and get more of an intuition of where this algorithm is going wrong. So for example, our algorithm looked at this digit and called it an 8, and that was incorrect. And it looked at this digit right here and called it a 1. I'm not even sure what that one actually is. So I'm not going to fault our algorithm for getting that one wrong, because I don't think a human would get that right. So you can look through and you can kind of get a hint of where your algorithm is right and where it's wrong. And from this, you might be able to iterate and choose something more sophisticated that would do a better job. And again, this is just the logistic regression is a really, really simple algorithm. And if you do something more sophisticated, you can get better results out of here. So hopefully that example gives you an idea of something more interesting you can do with these tools and kind of whets your appetite a little bit so you can think about how you could start applying this to data that you're working with. Right now we're going to take about let's say a 10-minute break. I just want to give people a chance to hit the bathroom and get a drink of water. And we'll come back, and what we're going to do in the second hour is talk a little more in depth about support vector machines and random forests and what's going on in those algorithms, because they're 2 of the more important supervised algorithms. So be back here at, say, 11:12. You're given a set of data. You want to figure out how to draw a line, essentially, that separates these data. So a support vector machine is fundamentally a way to draw a line or a hyperplane between sets of data in multiple dimensions so we can figure out whether the data lies on one side or the other. So this is the data we have. And you might think, if You might think, well, okay, I'll just draw a line. And if we do this by hand, we can see that there are a fair number of lines that perfectly separate these two data sets, right? And now the problem is that if you have a point that's right here, if you have a new point that's right there, and you want to ask, should I label it pink or should I label it yellow? The label of this point will depend on which of these three lines you draw, right? So just intuitively, how might you address this if you were trying to do this just looking at this yourself and not relying on any algorithm? How might you quantitatively choose between one of these three lines or any of the infinite lines between them? You have any ideas? Yeah, that's a question. You could get more data, and that would narrow it down. But still, even if you fill in more data, you're going to have some very small infinity of lines that you could choose, right?
Somebody else said maximize the distance from the line between some points.
Yeah, maximize the distance. So you could, so you could actually take the line itself and maximize the distance between all the points. That would be an interesting way. And that's I think stochastic gradient descent does that. Any other ideas about how you might do it? Yeah.
You can average each one of the clusters and then take the line perpendicular to the
Yeah, that's a good idea. So you could average the clusters and then actually draw a perpendicular line. That's so there are all these different ideas, and this is actually I imagine, I'm not a machine learning researcher myself, but I imagine this is what machine learning researchers do. They go, oh, we could do it this way. Let me publish a paper, and then 20 years later, everyone's using their method. What support vector machines does is it actually looks at the space between the clusters. So for example, instead of looking at the distance to all the points, like stochastic gradient descent, it looks at just the distance to the closest point. So this line is not very good because it comes very close to that pink point and very close to this yellow point, right? And this other line is not good because it comes close to the pink point on this side and close to the yellow point on that side. So you'd say this middle one is a little bit better because it kind of has a bigger buffer between it and the data sets, right? So this is essentially what support vector machines does, is it takes a look at all the possible lines that you can draw between the two sets of data and maximizes for this buffer between the data. So you can see that this middle line here has a much larger buffer than either of the other two lines. And for that reason, that's the one that support vector machines will produce. And it's a little more involved than that because sometimes the buffer can actually overlap the data. But at the very basic level, what support vector machines are doing is they're proposing a model that tries to intuitively do this, that tries to maximize some buffer between the data. And we can, as we saw before, we can fit a support vector machine by importing the model. We instantiate it with some sort of hyperparameters. We'll just choose a linear kernel here. We'll talk about that later. And then we fit it to the data. And then just to help us visualize this, I have this function that plots the decision boundary. So this is the actual model that the support vector machine comes up with for this data set. It draws a line down the center, and then it has these things at the edge, these buffer regions at the edge that it tries to maximize the distance between. And the thing that's interesting about these is that support vector machines, and this is actually one of the reasons that it's so powerful, it doesn't really care about the data set as a whole. It only really cares about these interior points that are right near the middle. Right, and these interior points is where this algorithm gets its name, the support vector machines. These interior points are called support vectors because they're like vectors in space, and they're the ones that actually support the model. So if you move these points on the outside around and move these points on the outside around, it essentially doesn't change the model unless you cross the boundaries or unless you move one of these points that's circled. So that's where the term support vectors come from, because you have these very few vectors that are supporting the entire model. And we can kind of see this in action in an interesting way. If we have this, in IPython we have this widget formalism. So what I can do is start adding points to the model, and you'll see that add points on the outside, it doesn't really change anything, but it's only when you add points towards the middle that things change. And I told you that notion of like an empty margin is a little bit of an approximation. So you can actually have support vectors that are within that margin under the model, because it's a little more complicated than the intuition I gave. But that's basically what it is. You have these points towards the middle, these important points that support the model, these support vectors, and the points towards the outside don't really matter anymore. And for various reasons, this turns out to be one of the fundamental reasons that support vector machines are so powerful. For one, like if you have a super outlier, like if you have a pink point that your instrument goes haywire and it gives you a value of 100, that outlier won't affect your fit at all. If you try doing something like a linear regression, that outlier is going to hugely affect your fit. Right? So support vector machines are nice in that way. But there's a problem here, right? The whole time I've been talking about these nice linear fits to data. And a lot of data doesn't have a nice linear fit. So for example, let's say our data set looks like this. This is a little bit contrived, but it's kind of an example of a type of case that might come up. And if you ask support vector machines to draw a line that discriminates between yellow and pink, it'll happily do that, but it'll give you garbage, right? So this is the line that support vector machines use for this data. So this is an issue, right? We can't fit a simple support vector machine if we have a nonlinear boundary like this. And where we can move forward on this is something called a kernel method. So that if you hear about kernelized support vector machines, this is the idea that we're going to develop right now. So a kernel method would say, let's transform this data in some way so that we can actually use a linear support vector machine and create this fit, right? So one example of a model we could use is called a radial basis function. So we just look at we do the exponent of the distance of each point from the origin, right? So this is the point at the origin, and if we look at the distance from the origin of each point right here, that's like one extra dimension we can add that might give us some interesting things to do. So for example, here's the 3D plot of if we take those initial dimensions. So here's our initial data right there, and we added a point that's the radius of, or we added a dimension that's the radius of each point from the center. And you can see that if we tilt this all the way up right here, oh, I tilted it too far. Let's tilt it right to 0 degrees. That radius actually gives us a perfectly linearly separable data set, right? So now in this 3D space, we can draw a plane straight through across that radius, and we can separate out the stuff in the middle from the stuff on the outside. And so this is exactly what, well, it's not exactly, but it's the idea behind kernelized methods. And when you fit the support vector machine with kernel equals RBF, which means radial basis function, what it does is it's actually much more sophisticated than what we did. We added one dimension. We pushed our data from 2 dimensions to 3 dimensions by adding this radius from the center, right? What the SVC kernel does is it computes the distance. It uses every single point in the data set as the origin and computes the distance to every point from it. So if you have 1,000 points in 2 dimensions, the kernelized representation of the data is 1,000 plus 2 dimensions, because you have a new dimension for each point in the data set with the information about the relationship between the other points and that point. And now you might think to yourself, like, well, this must be really, really slow, right? You're bumping your data up by 1,000 dimensions. And it is fairly slow, but it's not as slow as the most naive implementation would be. And there's this thing, if you ever want to like dive into the math of this and really be impressed, look up the kernel trick. The kernel trick is this very cool thing that comes up in machine learning all the time. And essentially, it's a way to let you do very high dimensional calculations in a low-dimensional projection. So if you know something about the mathematical properties of this kernel, you can do this operation really, really efficiently. And actually, the coolest thing about the kernel trick is that it allows you even to push the kernelized representation up to infinity dimensions. So there's some machine learning algorithms that actually are equivalent to doing computations in infinite dimensional spaces. But because of the kernel trick, you can do it in a finite amount of time. So read up about that. If you've heard about Gaussian process regression, the kernel trick is fundamental to that. And Gaussian process regression is basically an infinite dimensional regression that you accomplish through the kernel trick. So that, that's totally aside, but if you want to read about that, you should, because it's awesome. So if you do this kernel equals RBF and you fit it to the data, all of a sudden, magically, we find an SVM that fits this data set. And it does this by applying this kernel trick, transforming the data to a higher dimension, fitting a linear line in that higher dimension, and then collapsing it back to the original dimension, but in a way that's very, very efficient and doesn't actually compute that higher dimensional space. So this is one of the reasons that SVMs are so powerful, is because not only are they insensitive to outliers because of this like closest distance margin thing, but they also have a very efficient kernelized representation that allows you to fit really sophisticated models and really, really flexible models to your data. So I'm not going to go much further into SVMs than that, but I just wanted to give you an intuition into what they're doing, why they're so powerful, and then what this whole kernel thing is. And so now when you come across something where someone says, I'm using a kernelized SVM, my hope is that you'll say, ah, yes, kernelized SVMs. I know all about those. So any questions about SVMs? That was our brief walkthrough of support vector machines. Yeah?
Data systems, it sounds like kernelizing simply means adding another dimension to your data in some form. Is that?
Yeah, kernelizing means transforming, essentially it means transforming your data into a higher dimension of some sort. And whether that transformation explicitly happens depends on the algorithm, but most of the time you don't actually have to explicitly do that. Yeah. Yeah, Ro?
If there are overlaps of the data points, you can't get probabilistic. Is there a way to get a probabilistic?
Yeah, that's a good question. So he asked if there are overlaps in the clumps of data, is there a way to get a probabilistic classification? And there is in support vector machines. You have to actually instantiate it with probability equals true. It turns out that it's much more computationally intense to get out probabilities. So if you instantiate it with probability equals true, then you can do the predict proba to get out probabilistic predictions. But I'm not sure exactly what's going on under the hood, but it's more computationally intensive.
Quick question.
Yeah.
You said SVM is not sensitive to outliers.
Mm-hmm.
Can you explain it again? How?
Oh yeah. So let's go back to this picture. So the question was, SVM is not sensitive to outliers, and the intuition behind that is that basically it's only these circled points right in the middle that really matter for the model. So if you were to add another pink point that's above the screen, out of the screen here, it wouldn't affect the model. It's only these points near the margins that are supporting the model.
But if there's a yellow circle on the other side,
Yeah,
strong outlier.
that's true. So I glossed over that. He mentioned if there's a yellow circle that's on the wrong side, then there might be a problem, right? And yeah, so in that case, it is sensitive to those outliers. So it's not a magic bullet. None of these algorithms are magic. You actually have to think about what your data is saying. Yeah.
This is the whole point of the tool, the SVM, is to allow us to fit some radically different models per se, like are there any simple, like just quick tools in Scikit-learn to allow us to determine which one we might need? If we're dealing in 1,000 dimensions, we're looking at a graph. So
Yeah.
quickly available.
That's a good question. So the question was, are there tools in Scikit-learn to figure out whether we need a linear model or a kernelized model? And basically, what the tools there are these things that I've mentioned previously, the cross-validation. So that's a model selection question. If you want to quantitatively ask, does a kernelized model fit better than a linear model? That's a model selection and a cross-validation question. And if you go to the extended version of this tutorial, there's some information on that. Yeah, one more.
Does the SVM implementation in Scikit-learn have a Slack variable built into the margin?
Yeah, so the question is there a Slack variable built into the margin? This implementation is actually built on a C library called libsvm that a lot of other implementations use as well. So if I can never remember exactly what all of these mean, but I think the C value is the Slack value that you're talking about. And there are other little adjustments in there that you can read about in the documentation if you're more familiar with SVMs. So if you take a look at the Scikit-learn documentation, hopefully that'll answer your question better. All right, we have about 20 minutes left, which is the perfect amount of time to take a look at random forests now. So just like we took a quick in-depth look into support vector machines, I want to take a quick in-depth look now into random forests, which, as I said before, I feel like random forests are one of the most useful techniques in machine learning. Number one, because they're extremely flexible. They can fit just about any model if you do it carefully. And number two, they're extremely fast. They're basically the training and the training of these and the prediction of these can be done in an embarrassingly parallel way. And actually, under the hood, Scikit-learn uses some parallel architecture. And you can do things like, if you have a computer with 16 cores, the random forest implementation will actually use all those 16 cores if you tell it to. I should mention this random forest implementation is, I think it's pretty good. It was actually completely redone about a year and a half ago by a French guy named Gilles Loup, who was just finishing his PhD in random forests. Like he did his PhD on extensions of random forests. And in the process, as most PhD students do, he decided to procrastinate and completely rewrite the Scikit-learn random forest implementation. So it's really slick and really fast. And it's really interpretable too, which is pretty nice. So let's think about random forests. So what random forests are built on is this concept of a decision tree. And a decision tree is really, really easy to wrap your mind around. It's just a bunch of binary questions that you answer yes or no to. So for example, if we want to classify an animal, we're out in the forest and we see an animal and we want to know what that animal is, we might ask ourselves a series of questions. How big is the animal? Is it greater than 1 meter or less than 1 meter in size? So I'll say it's greater than 1 meter. Now, does the animal have horns? Yes or no? We'll say, no, the animal doesn't have horns. And number 3, is the animal wearing a collar, right? And the answer is yes. And you look at that, and you go down, and all of a sudden, with just 3 simple yes or no questions, we're pretty sure that this is like a big dog or something that's out in the woods, right? And this is the power of these decision trees. You're reducing with a single question, you're reducing your set of possibilities by a factor of 2 if you build it right. Now, the real question is, for any application, how do you build a good decision tree? Like, how do you decide which question to ask first and things like that? And there's this decision tree algorithm in Scikit-learn that actually does that for you and asks these questions for you. So this might be the data we're looking at. We have 4 different classes of data with 2 observations, 2 dimensions of them. And we're going to start building a decision tree to classify, to figure out whether a new point is red or yellow or purple, etc. So how do you decide which questions to ask? And this is what the decision tree formalism does. It basically says, well, I'm gonna split on one axis or the other, and I'm gonna figure out where at each step is the best possible split. So at the first step, you can make the most sense of the data by splitting along this black line right here. And the reason for that is that all the points above it are red, and all the points below it are not red. They're other colors. And if you look at this data, that's kind of intuitively it makes sense that if you're going to draw a single horizontal or vertical line through these to try to start learning about which is which, the red data here is probably the easiest to split off with a single line. And under the hood, the Scikit-learn decision tree estimator is actually doing a quantitative calculation, comparing all the possible splits and figuring out which is best. And it does that in a variety of ways, which you can read about in the documentation. So what the decision tree then does next is that it looks at each of these levels and applies the same logic and says, where should I split this? And so here it says the top level, everything's red, so I don't need to split it anymore. I'm basically done. The bottom level, well, if I split right here, then everything over here for the most part is yellow, and everything over here is not yellow. And now you might be able to guess where the line would go in this blue region in the next level. The line goes there and splits the blue from the purple, and here it splits the yellow from the kind of mix of stuff. And then the next one, it'll do further splits, and so on. And as you take these binary splits, eventually you kind of partition the parameter space into this area where you can ask what the prediction is. Right? I think that's as deep as this decision tree goes. So that's how a decision tree works on data. You're basically taking a series of yes or no questions, splitting the data along an axis. And because it's split along an axis, it's really, really fast to compute. So does anyone see a problem with this, though? Or you see some areas of the plot that are not very well, not very good decisions? The one that always sticks out to me is down here. Like, because of this little point right here and because of the way that we split it, it's going to call anything in this little strip purple. Like even a point down here at the bottom of the plot, it would call it purple because of that little point right there. So that's an example of overfitting the data. We've basically taken this one data representation and we've kind of overfit it, and we get some weird little things that may not actually reflect what's going on. So, and we can see that now if we can see this overfitting if we try several different subsets of the data. So here's one subset of the data, and this is the classifier we come up with. Here's another subset. We get that purple stripe back in there. And if you compare the two of these, they're broadly the same. The bottom right is always teal in both of these. But the details at the intersections, at the boundaries, are different. Right? So this is a classic overfitting thing. If you slightly change the data, the model changes like crazy. And so this is a problem with decision trees. You end up with these very fragile models at the boundaries of sets. So the question is, what do we do from here? Decision trees are great because they're intuitive. They're really blazing fast. You're just asking a bunch of binary questions about the data. But you end up in a situation where the model is really fragile and really depends on the inputs. So this is where the idea of random forest comes in. So the idea is, instead of looking at a single decision tree, you look at an ensemble of decision trees and you average out what they're telling you. So on average, these two decision trees would always tell you that this bottom right corner is teal. But in the middle, the sort of noise that you have would be averaged out between them. So to motivate this, if we take here, and what I'm going to do is I made the data overlap a little bit more to make this more interesting. And what I'm doing is taking a different subset of the data each time and fitting a decision tree classifier to it. And you can see as we change the random seed and take a different subset, you can sort of see by eye which areas are essentially the same and which areas are changing from time to time. And the intuition here is that if we automatically average over all these different realizations, we'll get out a classifier that's better than any of the inputs. It's better than any of the individual trees if we average them together. And this idea of ensemble sampling, or another way of putting it is bagging, is something that comes up a lot in machine learning. And actually, if you've heard of the Netflix prize, it was this very famous contest where Netflix basically put out all their data and said, hey, we want teams to come and build a recommendation engine so that we can recommend our users what movie they'd want to watch next. It turned out that I forget the exact numbers, but after a certain amount of time, there were these top 8 or 10 algorithms that people had put. And there was like this leaderboard thing, so in real time you could see who was doing better. And someone got the idea of taking the top 10 algorithms and averaging them out, right? And it turned out that the average of the top 10 algorithms was better than any of the individual top 10 algorithms, right? So this is really kind of a deep thing in machine learning. A lot of times, if you do it correctly, if you're averaging out these algorithms, if you bag them together and ensemble sample them, you end up with a better estimator. So that's where random forest comes from. So you probably see where this is going. The decision tree classifier is something in Scikit-learn. You wouldn't want to have to make 1,000 decision trees by hand. So that's why Scikit-learn has this random forest classifier. And it looks just like everything we've seen before. You import the classifier, you instantiate it, and you tell it what hyperparameters you want. And then we're going to visualize the tree here. And we can see that this is the result for this data set that the random forest classifier comes up with. So basically, after it averages out all those individual decision trees, it comes up with a decision boundary that's much closer to what we would draw by hand if we were just looking at this two-dimensional data. But of course, like I was saying before, the strength is that this generalizes up to thousands of dimensions. So you don't need to do it by hand. One question?
So this is a cool visualization. Is there, typically you have a lot more dimensions.
Yeah.
Some trick or recommendation where you can visualize more dimensions?
Yeah, so the question is, can you visualize this in more dimensions? It's hard to visualize much beyond 2 or 3 dimensions, and that's why when you start getting into, so I'm doing a lot of this visually because it's more intuitive, but when you start getting into actual machine learning practice, you tend to do things like compute cross-validation scores to sort of get a sense of how well your model's fitting the data. Because when you have, like you said, when you have 1,000 dimensions, it's difficult to just visualize it.
By saying average, is it actually like a voting?
What's that?
By saying average, is it actually a voting? Like each tree votes its own class for?
Yeah, that's basically what it is. We take the majority. There are different ways to combine it, but the basic random forest is you take the majority vote at each place. And you could think about this too. It also gives you a way to get a probabilistic prediction out, because if 800 of the trees say it's class A and the other 200 trees say it's class B, then you have kind of an 80-20 chance in your prediction. So it's really, like I said, one of the nice things about random forest is it's really intuitive and you can kind of dig into the model and see what's going on. But it's also very, very flexible and it's also very, very fast, which makes it nice. So I was talking here about random forest for classification, but it turns out you can actually use random forest for regression as well. And so one example, this is an example that I like. I took from Gaël Varoukou, who's a French Scikit-learn contributor. If you have data that looks like this, and you want to fit a trend to it without knowing much about what's going on, a linear model, right, would just draw a line straight through it. And you could move to like polynomial regression and kind of get some better trends. But random forest actually gives you the ability to fit these really subtle contours in the data. So if we apply a random forest regressor to this, we see that this is the output. The red model there is what the random forest fits. The blue is the actual data points. And this gray model that you can barely see is the generating model underneath. So you can see that random forests are even flexible enough to pull out this essentially dual frequency sine wave, right? We have a long-term trend and then an annual trend that you can fit. So it just shows you the flexibility of random forests, even for a regression task like this. And the other thing, we were looking at the digits classification earlier. And just to remind you what we were looking at, if we have these are the digits that we were seeing. And last time we used a logistic regression, which was a very basic model. If we use a random forest regression, we can see that we don't, oh, this is a decision tree. If we just use a decision tree classifier, we get an accuracy of about 84%. But if we move to using a random forest classifier, we can do much, much better. And actually, this is kind of the final exercise of the thing. I laid out all the code here to fit the decision tree classifier, to predict the results, to get the accuracy score, and then to visualize the confusion matrix about what's getting confused here. And the question is, if you, instead of using a single decision tree, if you use multiple decision trees in a random forest, can you do better? So I want you to, we have about 5 or 10 minutes left before we're going to break for, I think lunch is next. And in that time, see if you can get started on this and trying to apply a random forest to this data and see what level of accuracy you can get with your random forest by tweaking those hyperparameters. So I think this is a really striking example of this. If you can just copy and paste this, basically these 4 lines from up here, and take a look at this. And if you put number of estimators equals 1, you get an accuracy of 78%. So that's a single decision tree. But now if you average, say, 100 decision trees, you're up to 97.5%. And if you average 1,000 decision trees, it's going to take a little while longer. That's about the same, 97.7%. So we can get, with this random forest classifier, we can get 98% accuracy of classifying these digits, which is pretty cool, I think. Because it's so intuitive, it's so fast, and it really lets you see what's going on under the hood. And it's embarrassingly parallel. So if you have 32 cores that you want to use, you can use all those cores for this fitting. So I realized that this was a little bit of a quick breeze through a lot of this stuff. We've spent almost 2 hours talking about machine learning and going into depth on some of these things. I'm going to be around for the rest of the weekend if you want to catch me in the hallway and ask questions. But I hope this was helpful, and thanks very much. Enjoy the lunch and enjoy the rest of the conference.